Okay, let's finish up diagonalization. Next on the menu is Theorem 5.3. So we've gone through an example of how to diagonalize. What we're looking for is some conditions under which a matrix is diagonalizable. Theorem 5.3 is called independence of eigenvectors, and it says the following. Let A be an n by n matrix. Of course, it has to be square to talk eigenvalues and eigenvectors. If v1 through v sub n are eigenvectors of A, corresponding to distinct eigenvalues, lambda 1 through lambda sub n, then the set v1 through v sub n of corresponding eigenvectors is a linearly independent set. If it's a linearly independent set, we know A is diagonalizable. We know we'll make matrix C with columns as these eigenvectors. Linearly independent columns implies an invertible matrix, and you're often running for diagonalizability. So the real punchline here is, if we've got distinct eigenvalues, then we've got a diagonalizable matrix. I mean, the piece of the claim we're about to prove is distinct eigenvalues imply linearly independent eigenvectors. So let's look at a proof of that. Okay, here we're going to go through and give a proof by contradiction. So what we're going to do is suppose the conclusion is false, the hypothesis is true, and show that leads to a contradiction. So our supposition of a false conclusion has to be incorrect itself, and the conclusion in the statement must be accurate. So what we're working on is, if the eigenvalues are distinct, we want to show that the corresponding eigenvectors, v1 through v sub n, are linearly independent. Okay, so what we're going to do is suppose the eigenvectors, to the contrary, are linearly dependent. Suppose v1 through v sub n is a linearly dependent set. So that's the big assumption we're making, and it's wrong because we're going to derive a contradiction. Okay. Page 203, number 37, allows us to translate a property of a dependent set of vectors into a specific kind of linear combination, a specific dependence relationship. If these vectors are linearly dependent, then there is a value k such that v sub k can be written as a linear combination of v1 through v sub k. So we've gone through this list of vectors, and we found the first vector in the order in which they're listed that can be written as a linear combination of the previous vectors. If it's the first one, then that previous collection of vectors must be linearly independent, because equation 2 here implies a dependence relationship on the first k vectors. I don't know what k is. Have to be at least 2, so we've got vectors on both sides, and for all I know, it could be as large as n. I don't know unless I know more specifics on the vectors. But if we have a linearly dependent set of vectors, there is a vector k, a first vector k, that can be written as a linear combination of the previous k minus 1 vectors. Nothing special about eigenvectors, just a property of linearly dependent vectors. Okay, maybe a quick observation. These coefficients, d1, d2 through d sub k minus 1, they ain't all 0. They couldn't all be 0. If they were all 0, then v sub k would be the 0 vector, and v sub k is an eigenvector, and so it's not a 0 vector. So I can't put my finger on these coefficients, d1 through d sub k minus 1, any deeper than to say they ain't all 0. Okay? So what we're going to do is take this equation 2 and do 2 things to it. We're going to multiply both sides by lambda sub k, and we're going to multiply both sides by matrix A. First, multiply both sides by lambda sub k. We'll get a lambda sub k in front of the v sub k. We'll distribute the lambda sub k's throughout here. Where we're going on this might be a little vague, though the argument you should be able to follow. Lambda sub k times v sub k, I know what that is, because lambda sub k is an eigenvalue and v sub k is a corresponding eigenvector. So we got a particular expression for this. This is equal to matrix A times vector v sub k by the very definition of eigenvector and eigenvalue. Oh, speaking of, probably come back and look at this equation in a second. Let's apply matrix A to both sides of equation 2. Let's go back. Here's equation 2. So we're going to put a matrix A here, a matrix A that we can distribute here. We can pull scalars through. We'll have A times v sub k. But v sub k is an eigenvector. That equals lambda sub k v sub k. We'll have A times v sub 1. But v sub 1 is an eigenvector. We'll have lambda sub 1 times v sub 1. A times v sub 2. But v sub 2 is an eigenvector. So we'll have lambda sub 2 v sub 2. And that little step of algebra has been skipped. We're applying A to both sides. A times v sub k is lambda sub k times v sub k. Remember the very definition of eigenvector and eigenvalue that we have down here. We had A times v sub 1. Okay, that's the same as lambda 1 times v sub 1. So we're changing the matrix multiplication for this scalar multiplication, which you can do because you've got eigenvalues and eigenvectors. Do that throughout on the right-hand side. Now we've got lambda sub k, v sub k on the left-hand side, and some stuff here on the right-hand side. We're going to subtract this equation 4 from the previous equation 3. Okay, equation 3, hey, it's got lambda sub k, v sub k on the left-hand side too. So when we subtract, we'll get the 0 vector on the left-hand side. From d sub 1 lambda sub k, v sub 1 plus d sub 2 lambda sub k, v sub 2, and so forth, we will subtract this, d1 lambda 1 v1, d2 lambda 2 v2. In equation 3, we had lambda sub k's for all these coefficients. So when we do the subtraction, we've got lambda sub k, v sub k on the left-hand sides. Do the subtraction, you'll get a 0 vector on the left-hand side. On the right-hand side, we had d1 lambda sub k v in equation 3. In equation 4, we've got d1 lambda sub 1 v sub 1. So do the subtraction, we'll get d1 lambda sub k minus lambda sub 1 v1. d2 lambda sub k minus lambda sub 2 v2. So what will happen is we keep lambda sub k as this first term. The coefficients d1, d2, and so forth run through their values. And we'll be subtracting off lambda sub whatever, where the subscript is the same as what we have as a subscript for the vector v and the coefficient d. So all these terms are of the same form. All right, we got a linear combination of vectors here set equal to 0. And remember, we got into this by that number 37 or whatever it was, with the assumption that v1 through v sub k minus 1, those vectors are linearly independent. Well, we've got a linear combination set equal to 0, the 0 vector. This is the dependence relation unless all these coefficients are 0. And we got a problem. We can't have a dependence relation on a collection of linearly independent vectors. Okay? Well, we already said the d sub i's, they're not all zeros. I don't know what they are, but they ain't all zeros. How about the lambda sub k minus lambda sub 1? What were our hypotheses? Distinct eigenvalues. Okay, well, if the eigenvalues are all different, then lambda sub k minus lambda sub 1, that ain't 0. Lambda sub k minus lambda 2, non-zero. All the differences of lambdas are non-zero because all the lambdas are different. So we've got some of the d's being non-zero and all of the lambda sub k minus lambda sub whatever's being non-zero. So for sure, not all of these coefficients of v1 through v sub k minus 1, not all of those are 0. In other words, we've got a dependence relation on v1 through v sub k minus 1. But we got to this stage by knowing v1 through v sub k minus 1 was a linearly independent set. You can't have a dependence relation on a linearly independent set. That's the contradiction that says we've assumed something that must be false. We assumed that the vectors v1 through v sub n were linearly dependent. That's the assumption we made. That's wrong. It must be the case that vectors v1 through v sub 1 are not dependent, that is, they are linearly independent. And that's what we were trying to show. Different eigenvalues yield linearly independent eigenvectors. Okay, so back to the notes briefly, I'll illustrate it. So here's what good that is. So if you want to show a matrix is diagonalizable, if that's all you want to know, you don't maybe want to know how to diagonalize it. If you just want to know, is it diagonalizable? We could get away with just showing the eigenvectors are all different. That'd do, according to Theorem 5.3. That'd allow us to draw the conclusion, A is diagonalizable. So let's check out number 6, back to the supplements. Whoops, number 6 says, find the eigenvalues and corresponding eigenvectors. So this will take a while. This 3x3 matrix. Find an invertible matrix C and a diagonal matrix D, the usual relationship, D equals C inverse AC. All right, the only thing, if I meticulously read the instructions, they didn't ask us to find C inverse, but they asked us to find everything else. So we won't find C inverse. I know it exists. We've got theory that tells us it's going to exist. Okay, so off we go. We need the eigenvalues. So we'll take A minus lambda I, matrix A, subtract lambdas down the diagonal. We'll take the determinant of that. That'll give us the characteristic polynomial. Determinant of A minus lambda I is this thing here. You see any shortcuts? You don't see any entries of 0, so I don't see any shortcuts. We can expand along any row or column, and it doesn't look like it much matters. Looks like we've expanded along the first row. So do your expansion along the first row, you know, the plus, minus, plus story, the entries in the matrix, and then the determinants of the associated minor matrices. We're well into this. There you go. There's the arithmetic. Multiply out and factor. It needs to factor cleanly or we're stuck. The ones in the book will factor cleanly. The ones on the test will factor cleanly. So we get, for the characteristic polynomial, negative lambda plus 1, lambda minus 2, lambda minus 3. For the eigenvalues, we'll set that equal to 0 and get negative 1, positive 2, and positive 3 as the 3 eigenvalues. Okay, set the characteristic polynomial equal to 0. That produces, let's subscriptum, lambda 1 is negative 1, lambda 2 is 2, lambda 3 is 3. Subscriptum, where larger subscripts are associated with larger eigenvalues. That was just sort of my standard operating procedure, just to be consistent and put us on the same page. Order doesn't matter here, but that's potentially going to affect some of the answer down the road. Another reason to try to put us always on the same page with the order in which we list these. But order isn't essential, but I've got my plan. All right, how are we doing? Is this going to be diagonalizable? Yeah, it was a 3x3 matrix, and it's got 3 different eigenvalues. The eigenvalues are distinct, so Theorem 5.3 will tell us then that the corresponding eigenvectors will be linearly independent, and we're good to go. That means that matrix C will be invertible, and we can diagonalize this. All right, but right now the distinct 3 different eigenvalues for 3x3 matrix, diagonalizable. Okay, let's find those eigenvectors because they told us to do that. All right, let's take a little while. Lambda 1 equals negative 1. Okay, we'll take as a corresponding eigenvector, let's denote it V1 vector. You know, it'll have the usual components. That leads us to consider the associated homogeneous system of equations. And this is a part where I say, you better get, in this system of equations, you better get a free variable. Don't make me come out there. Because if you don't get a free variable, something's wrong. You know this is going to produce a free variable and a whole family of eigenvectors. You don't get a free variable, something's wrong. You probably don't really have an eigenvalue. Okay, so with lambda equals -1, we subtract -1 along the diagonal. Of course, that corresponds to adding 1 along the diagonal. I'm augmenting with zeros because I want it to look like a system of equations. You might argue, no, you don't need to keep up with those zeros because they ain't ever going to change. You know, well, I'm going to put them there anyhow because I want to be thinking system of equations. And true, they never change. So we'll take this coefficient matrix, put it in reduced row echelon form, I guess. I already see the second and third rows are the same. Excellent. That'll produce a row of zeros, and I know we're going to have at least one pivot-free column. Perform the row reduction. There's the steps and the details. I leave it to you to hack through all the arithmetic. We'll end up, apparently at this point, where we've got in the coefficient matrix, yes, one pivot-free column. That means one free variable. We'll translate the augmented matrix back into associated system of equations. We'll solve for V1, V2, V3. We'll introduce R equals V3 in this case. That's a free variable. That'll produce V1, V2, V3 of this form where R can be any real number. All right, then the corresponding collection of eigenvectors is R times the -5, 2, 1, the coefficients we had before. R can be anything. It can't be 0 for reasons elaborated on extensively. You can't use the 0 vector as an eigenvector. Okay, so that takes care of the first eigenvalue. Now we're going to need to run back and pick one eigenvector from this infinite collection of eigenvectors. How about we let R be 1? If we let R equal 1, then we'll use the obvious thing, -5, 2, 1. You want to use R equals 3 and take the vector -15, 6, 3. Ain't nobody can stop you from doing that. It's an eigenvector as well. You can use any eigenvector you want corresponding to this lambda sub 1 eigenvalue. Of course, let's make it easy on all of us and choose the easiest one, which would be R equals 1 in this case. Okay, do it again. Lambda 2 was 2. Okay, we'll do A minus 2 A minus 2I, it should read. And we'll subtract 2 along the diagonals. Okay, we're considering a system of equations. We'll do the row reduction. Looks like we'll end up here. And pivot-free column. There'd better be a pivot-free column. Change it back into a system of equations. Solve for V1, V2, V3. Introduce a free variable. Produces this. Next slide, we'll turn that into the form of eigenvectors. So for lambda 2 equals 2, we get eigenvectors of the form scalar multiple of -3, 1, 1. Any scalar except for 0, of course. So pick one. How about we let S be 1? And we'll pick -3, 1, 1 as a specific eigenvector. And that's what we'll use when we create matrix C. So I bring up pick one because we're making a matrix with these eigenvectors as columns. You can let S be something other than 1 if you want. Gives you a different looking answer, but also a correct answer. Lambda equals 3. Okay, same stuff. Subtract 3 along the diagonal. Do the row reduction. Pivot-free column. Here comes changing it into system of equations, introducing a free variable. Let's see, you did a little trick here with a free variable. The book does this all the time, where we're letting t be v3 divided by 2, because there's a v3 divided by 2 that pops up here. Cross multiplying, you'll have v3 equals 2t. So when I substitute for the v3s, I'll replace them with 2t's throughout. It gets rid of the fraction here. You don't want to get rid of the fraction there. You go right ahead. You may not want eigenvectors with fractions in them, but you could take care of that at this stage. So we get v sub 3 is t times -5, 2, 2. If we hadn't made that little trick with v3 over 2, you'd have -5 halves, 1 and 1 times t. I might just pick t to equal 2, and that'd get rid of the 1/2, the -5 halves, get rid of the half part, and you'd end up in the same place. So Matter of style if you want to eliminate the fractions on the previous stage or at this stage. If you're going to have to find matrix C and invert it, you don't want fractions in it. And this can always be done without fractions for the examples we'll see. So then we found all eigenvalues. They were distinct. We found all eigenvectors. Now let's go through and pick particular eigenvectors as commented. Let's let R, S, and T, the three free variables that we introduced, let all those be 1, and pick the corresponding eigenvectors. That'll give us eigenvectors of -5, 2, 1, -3, 1, 1, as mentioned earlier, and -5, 2, 2, and it'll always be what we've got sitting right here if you choose that free variable to be 1. And it depends how you set things up. Maybe you don't want to use free variable equals 1. I say you don't have to, but you definitely want integers. You want integers in those eigenvectors. All right, so Theorem 5.2 said, make yourself a matrix C and have this is the first column, this is the second column, and this is the third column. So I put these into a matrix as columns, right? That gives us matrix C. Order matters. We had a first one. So that first one corresponded to eigenvalue, -1. The second one corresponded to eigenvalue 2, and so forth. Here's matrix C. We've also got to make matrix D. Well, matrix D will have lambda 1, lambda 2, lambda 3 along the diagonal. So this is when the order matters. So we get the -1, 2, 3 along the diagonal in matrix D. If you swap the -1 and a 2, you'd have to swap the corresponding eigenvectors back here. Oops, it's gone. Back there in matrix C. Here it comes. So if we were to swap the 1 and the -2, so we're calling this one lambda 1 and this one lambda 2, yeah, you'd have to swap the orders of those corresponding eigenvectors. I'd say, please list the eigenvalues in increasing order, and then we're on the same page. So here's what we get for matrix C and matrix D. They ask us to find C and D. They didn't ask us to find C inverse. No big deals, just additional row operation stuff. But we knew this was going to work. It worked because Theorem 5.3 wasn't Theorem 5.3. These eigenvalues are distinct. So I guarantee you by Theorem 5.3, these corresponding eigenvectors are linearly independent. And so matrix C really is invertible. Back to the notes. Definition of similar matrices, and we've ran across ideas that look alike like this before. An n by n matrix P is similar to an n by n matrix Q if there exists an invertible n by n matrix C such that C inverse PC equals Q. That's the same kind of style we had when we dealt with diagonalizable matrices, sorry. So we could reword our definition of diagonalizable as matrix A is diagonalizable if it's similar to a diagonal matrix. So we had a diagonal matrix in one entry and matrix A in the other, and we had the C invertible matrix as well. Similar matrices are a common topic in a theory of matrices classes. How are you going to approach something like this? Well, if we wanted a diagonal matrix, we'd be good to go. And we'd use eigenvalues and eigenvectors. So I think we're not going to explore too much how to find C and C inverse for matrices P and Q. But we are going to use this similarity stuff in connection with eigenvalues and eigenvectors in terms of how those relate for matrix P and matrix Q. Specifically, number 18 says, prove that similar square matrices have the same eigenvalues with the same algebraic multiplicities. And we talked about algebraic multiplicities as a topic from high school algebra or from pre-calculus. And we talked about exercise 5.1, number 38 at some point. This is awfully similar to that. Okay, so suppose we consider C inverse AC minus lambda I. All right, so we'd be taking a matrix A and multiplying it by a C and a C inverse is given. So we're finding the eigenvalues and eigenvectors. So we're just finding the eigenvalues in this one, sorry. So we want to consider this. We've got a matrix. That matrix is C inverse AC. Subtracting lambda I. Now we're going to fiddle with it and see that we get something similar. We want to look at the characteristic polynomial and show similar matrices have the same characteristic polynomial. And characteristic polynomials are determinants of expressions like this. All right, let's take the identity matrix and write it as C inverse C, because we can, and we're looking for something to factor. We can factor a C inverse out on the left in both of these. Since we haven't done that yet, we can rearrange this. Scalars pull through, so I'm getting the scalar out of the way, then factoring out the C inverse on the left. All right, we've got C's on the right, so we can factor C's out on the right. Remember the little story about introducing an identity matrix there. And hey, look, we get an A minus lambda I. C inverse on the left, C on the right. We've done this before. That number 38 in the previous section worked like this. All right, so let's check out characteristic polynomials by taking determinants. Recall, and we've done this before as well, that the determinant of C inverse is 1 over the determinant of C. We've just quoted exercise 4.2.31, I guess, on that. It's a result that follows from the product behavior, the product rule of multiplication of determinants. But we've got that relationship, and so when we take the determinant of C inverse AC minus lambda I, that's the characteristic polynomial of matrix C inverse AC. We'll take a determinant then of the product, the multiplicative property, they call it, shows us that the determinant of the product is the product of the determinants. Here we've got a determinant of C inverse, so we'll get a 1 over determinant C here. Hey, that'll cancel with a determinant over here. These three things are just numbers. Determinants are just numbers. So we've had this conversation before as well. So we get cancellation and we get a determinant of A minus lambda I. Hey, that's the characteristic polynomial of matrix A. And this is the characteristic polynomial of matrix C inverse AC. That is a matrix that's, in our new vocabulary, similar to matrix A. The characteristic polynomial of A is the same as a characteristic polynomial of C inverse C. This is what a matrix similar to matrix A looks like. Our definition had P's and Q's in it, so we're using A's and this thing here, C inverse AC. So we've got two similar matrices. They've got the same characteristic polynomial. Well, them characteristic polynomials, and they're the same. They got the same roots, and they've got the same algebraic multiplicity of their roots. In other words, this matrix A and this other matrix, which is similar to it, have the same eigenvalues, and those eigenvalues have the same algebraic multiplicities. Similar matrices behave similarly with respect to eigenvalues and eigenvectors. Back to the notes, we need to explore this algebraic multiplicity stuff a little bit more. The algebraic multiplicity of an eigenvalue, lambda sub I, of a matrix A is its multiplicity as a root of the characteristic equation of A. So if we just get linear terms, all them eigenvalues are multiplicity 1. If we get a linear term squared, then we've got an eigenvalue of multiplicity 2. It's the exponent that goes on that linear term. The second example we did, I think in the previous section, we had an eigenvalue of 4, and its algebraic multiplicity was 3. We had a lambda minus 4 cubed. I think that was, or maybe negative of that, was the characteristic polynomial. So that was an example of a single eigenvalue of algebraic multiplicity, more than one. It was 3 in that case. The geometric multiplicity, on the other hand, is the dimension of the eigenspace associated with that eigenvalue. All right, now where's this stuff coming from? Remember, whenever we had a single eigenvalue, we went through and not always, but more often than not, we had a single independent variable associated with the system of equations that led us to the eigenvectors. So when we had eigenvectors, they were scalar multiples of some given vector. But one time, it's back with that example where we had 4 as an eigenvalue of multiplicity 3, and that's why I did that one. It illustrates a lot of this stuff in hindsight. If you look back at that example, we had an eigenvalue of algebraic multiplicity 3, and when we went through and saw the system of equations, we didn't have 3 free variables, we only had 2 free variables. And I complained about it at the time. It seems like something was missing. We started with a 3x3 matrix. We had the same eigenvalue, but it counted 3 times. But then we ended up with only 2 free variables when we were looking at systems of equations. That 2 would represent the geometric multiplicity of that particular eigenvalue. So it's dimensions of eigenspaces, and we haven't done big examples of these, but when you find a basis for the eigenspace, that's when you're finding the free variables and those little vectors that the free variables are multiplied onto. You got 2 free variables, you got a geometric multiplicity of 2. You got 3 free variables that comes from one of these systems of equations, you will have 3 linearly independent eigenvectors, and they will reflect the geometric multiplicity of 3 for the corresponding eigenvalue. A little result I don't think we'll actually use too much. The geometric multiplicity of an eigenvalue of a matrix is less than or equal to its algebraic multiplicity. That was illustrated in that one example from the previous section. We had a geometric multiplicity of 2 and an algebraic multiplicity of 3. If you think back to that one. The proof of that is to be given as an exercise. Something more useful is the following. If an n by n matrix A, or excuse me, an n by n matrix A is diagonalizable, if and only if the algebraic multiplicity of each eigenvalue is equal to the geometric multiplicity of each eigenvalue. We might have eigenvalues being complex, might require eigenvectors being complex as well. Let's gloss over that. See chapter 9 for more details on complex stuff. But this means, in some sense, we'll have the characteristic polynomial being degree n, because we've got an n by n matrix. So the algebraic multiplicities will add up to n. If the geometric multiplicities add up to n as well, you're good to go. Because guess what? You can make matrix C having as its columns eigenvectors. And you got enough eigenvectors to do that. And they will be linearly independent. That's the real claim of this theorem 5.4. All right, let's use that. Let's look at number 10. A little foreshadowing. In this example, we have an eigenvalue of algebraic multiplicity 3 and only geometric multiplicity 1. Oh, well, according to theorem 5.4, then that matrix, it ain't diagonalizable. You got algebraic multiplicity 3. You need geometric multiplicity 3 to have a diagonalizable matrix. So let's take a look at that one. Okay, number 10. And the good news is, I think it's only got one eigenvalue, so the computations won't be quite as ugly. Okay, determine whether this matrix A is diagonalizable or not. Oh, awesome. They don't want us to actually find C and all that stuff. Okay, so let's see what happens here. Let's find eigenvalues first, because that's how all these start. So we'll take A minus lambda I. That's this matrix with lambda subtracted along the diagonal. I think that's the first time I haven't spelled that out in great detail. Some good news here. Hey, that's an upper triangular matrix. Remember those guys? It's easy to take the determinant of an upper triangular matrix. We'll just multiply the diagonal entries together. You don't like that, expand it along the first column and this will happen. But we've taken advantage of upper triangular matrices before. So P of lambda, the determinant of A minus lambda I would just be 3 minus lambda times 3 minus lambda times 3 minus lambda. So that worked out really well. We've only got one eigenvalue, but because of that little exponent of 3 there, this is an eigenvalue of algebraic multiplicity 3. Sorry about all the 3's, but the exponent tells you the algebraic multiplicity. All right, that previous result says if the geometric multiplicity is also 3, we're good. And this is a diagonalizable matrix. All right, so let's check on eigenvectors and see how many we find up to linear independence. You know it's going to change into a system of equations, and we're looking for free variables. Okay, so we'll take vector v. We won't subscript it because there's only one eigenvalue. Didn't subscript the lambdas either. Let v1 through v3 be its components. So we need a minus lambda I times this vector v to equal 0. Corresponds to a homogeneous system of equations. The coefficient matrix is the a minus lambda I. All right, plug in lambda equals 3, produces this. Already I see a pivot-free column. Already, I like this one. We've already got it in reduced row echelon form, in fact. All right, so we've got one pivot-free column. That's going to mean one free variable. We'll go through it. That's going to mean geometric multiplicity of 1, and that's not enough. And we mentioned that in the notes. Okay, so we'll take what we had previously, write it back in terms of a system of equations. We get v2 equals 0, v3 equals 0, and 0 equals 0. Or v1 equals, I don't know anything about v1, so v1 equals v1. v2 and v3 are 0. Let r equals v1 be a free variable, produces this. I didn't know v2 and v3, but v1 could be anything. And so we get, for the eigenvectors associated with lambda equals 3, we get vectors of this form. Any non-zero scalar multiple of the vector 1, 0, 0. All right. Oh, but that's only geometric multiplicity 1. If we had 2 free variables, we'd have geometric multiplicity 2. That wouldn't be enough either because we had algebraic multiplicity of 3. So the algebraic multiplicity of the eigenvalue was 3, the algebraic multiplicity and the value of the thing, but the algebraic multiplicity was 3 because of an exponent of 3 on the previous slide. One free variable here, then the geometric multiplicity of this eigenvector is just 1. If we had 2 free variables, we'd have geometric multiplicity 2. If we had 3 free variables, we'd have geometric multiplicity equal to algebraic multiplicity, and we'd be in business. So say a theorem 5.4 for diagonalizability. But here, it didn't work. Geometric multiplicity is 1, algebraic multiplicity is 3. They're not the same, so matrix A is not diagonalizable. In a sense, there ain't enough linearly independent eigenvectors for matrix A. Back to the notes. Okay, let's see what we got here. Let's do one more definition and maybe a final example. Okay. Theorem 5.5 is cool because it's easy to read. You ought to know what the words all mean. The unfortunate property of this is you can't really prove this until chapter 9. We need to know more stuff about complex numbers. That's why the proof of this is in chapter 9. But the theorem, diagonalization of real symmetric matrices, is quite easily understood. It says every real symmetric matrix is real diagonalizable. So if the entries are real and it's a symmetric matrix, then it's diagonalizable. Real diagonalizable means all the eigenvalues will be real, All the eigenvectors will be real. Complex numbers won't even arise if we deal with real symmetric matrices. So, in other words, if A is n by n, of course, it has to be square. Symmetric with real number entries. Every eigenvalue is real, and its algebraic multiplicity equals its geometric multiplicity. Yeah, okay. Then there's enough eigenvectors, enough linearly independent eigenvectors for this matrix to be diagonalizable. It's easy to understand because you know what symmetric means. Diagonalizable, hopefully you got the hang of that by now. They throw the word real in there. Yeah, well, you know, complex numbers could be an issue whenever we deal with these characteristic polynomials, or any polynomials for that matter. So if we were to concern ourselves with some examples dealing with symmetric matrices, it'd be a good place to get some examples. Now, I'd still be terrified just to make up an arbitrary symmetric matrix, because who knows what the eigenvalues will be or if I'll be able to find them. I know they'll be real, but I might not be able to find them if I just willy-nilly make up numbers. So let's see, let's look at the last example. From this section, there's a couple of theorem type results in there. Let's go down to the last example. Here we go. Okay, it's an exotic setting. But not all vector spaces are Rn. This takes us back to, I think we saw an example in the previous section, back to the vector space D infinity of all functions mapping R into R that have derivatives of all orders. These are infinitely differentiable functions. So that's the reason for the symbol D infinity for the vector space. They give us a set of vectors. Okay, the vectors are functions that will probably come across as exotic in this class because you're used to vectors as just little square brackets and real numbers. But there's plenty of applications out there where the vectors aren't just square brackets and in numbers. The vector spaces aren't just Rn, they're more involved, they're more sophisticated. This is one of them. And this is useful stuff. This would pop up in differential equations, for example. Whether they couch it in the language of linear transformations and eigenvalues and all that, I don't know. But here they're trying to say, trying to have us show that the set e lambda 1x, e to the lambda 2x, up through e to the lambda kx. So these are exponential functions. They've got the exponents, multiples of lambda times the x's. And they're telling us that those lambda sub i's are distinct. The claim is that set of vectors is independent in the vector space D infinity of all functions mapping R into R and having derivatives of all orders. Okay, these sound familiar. Eigenvectors, as they meet linear transformations, would be something I would apply the linear transformation to and get a multiple of the input to that linear transformation. What's going to happen, our linear transformation here is going to be derivatives. What's going to happen when you differentiate e to the lambda 1x? You're going to get e to the lambda 1x times lambda 1, chain rule says. Well, we're just going to get lambda 1 times the vector we put in. Kids, that's eigenvectors and eigenvalues. And in the previous example, we saw it was closely related to this. Okay, so we'll introduce the linear transformation of differentiation. When you differentiate e to the lambda ix, you get lambda I e to the lambda ix for any of these I equals, what, 1 through k? Okay, so we've applied a linear transformation and we got a scalar multiple of what we put in. That scalar is called an eigenvalue, and that thing we put in, this vector, it's a function, but the functions are vectors here. This vector is an eigenvector corresponding to lambda sub I. Okay, so e to the lambda sub ix, this is an eigenvector of the linear transformation of differentiation corresponding to eigenvalue lambda sub I. The little relationship here doesn't look new to you if you've done calculus with exponential functions. Early transcendentals will do it in Calculus 1. And it looks like our stuff. It looks like our eigenvalue, eigenvector stuff. Here's the, I want to say matrix. It's not a matrix, it's a linear transformation. Bet you it's got some kind of matrix representation. Long story in this vector space, but it does. And then we've got a constant multiple of that input vector. That's us. That's eigenvalues and eigenvectors. Okay, so each of these vectors in this set of vectors is an eigenvector associated with different eigenvalues, because they told us all the lambda sub i's are different or distinct. All the eigenvalues are distinct. They told us that. So by theorem 5.3, the set of eigenvectors associated with them are linearly independent. And we're done, because all we had to do was show linear independence. A much more complicated way would be take a linear combination, set it equal to 0, and show all the coefficients must be 0. Well, here's a slicker way of doing it, which takes advantage of properties of eigenvalues, just as long as we use the right linear transformation of differentiation. Of course, this was designed with that in mind. But hey, we know when we have different eigenvalues, we get linearly independent eigenvectors. That was what 5.3 was about. We have different eigenvalues because they told us we did. The lambda sub i's are distinct. So the corresponding eigenvectors, linearly independent. You won't find a quicker way of establishing linear independence than this little approach here. Of course, it's designed to be worked that way. And I think that takes care of 5.2. Okay, classroom-wise, we're probably headed to chapter 6. I want to put together a little something on section 5.3, which has some applications in it. Probably not time to cover it in class, but I want to put it together anyhow. So I'll run work on that, and I will see you in section 5.3 or in chapter 6 as appropriate. Have a nice day.